Welcome and good afternoon. My name is Laura Heineck, and I am a member of the customer care team here at Vitek Corporation. I am very pleased to be your host for this webinar today as we discuss 9 laws of effective systems engineering. Before we get started, I would like to take a moment to review a few technical details. First, questions. Please feel free to submit your questions at any time via the Q&A function in the GoToWebinar window. We will be monitoring these throughout today's event. We plan to respond to questions at the end of the webinar, so please keep them coming. We probably will not have time to respond to all questions, but we want to know what's on your mind. Your questions will help guide our planning for upcoming webinars. Finally, recording. The webinar is being recorded today. If you're having technical difficulties during the presentation, an online archive with this presentation will be available within 24 hours of the live version. I believe that takes care of all of our housekeeping matters. Let's get started. I would like to take a moment to introduce Zane Scott, our speaker for today's presentation. Zane is the Vice President of Professional Services and Training Organization. For the past 30 years, Zane has built a skill set which enables him to provide insight and guidance to individuals and companies as they improve organizational processes and methodologies across their organizations. Zane is the author of numerous white papers, including one on today's topic, 9 Laws of Effective Systems Engineering, and is the co-author of Vitek's primer for model-based systems engineering. Please join me in welcoming our speaker for today, Zane Scott.
Thanks, Laura. And before I begin, a big thank you to you as our host and to Bethany Maddox as our recording engineer this afternoon. As Laura has told you, we are going to talk about 9 laws of systems engineering. We're very happy that you've taken the time to join us today, and I hope that you'll find this interesting and enjoyable. Systems engineering is critical. It's especially critical in today's economy where businesses need to refine the ways in which they do business as well as the end products that they deliver to their customers. In order to deliver the products that the customer needs, we need to maintain a systems view of our business processes throughout. Therefore, the ability to keep the system in view, the ability to use systems thinking and to engage systems engineering in the process is critically important, even in those areas of the business world where the term systems engineering is not known at all. The systems perspective keeps our efforts, whether they are design efforts or improvement efforts, from becoming lost. It keeps the design on track. As we maintain a systems view, we're able to maintain a view of the map from where we are now to where we'd like to be in terms of developing a product or in terms of developing a process or improving that process. It also allows us to work across disciplines without loss of focus. We're able to work from discipline to discipline and to speak the language of the multidisciplinary teams that are supposed to come up with the improvements or products that are the focus of our project. We maintain a systems view in order that we can keep projects and programs on track. What we'd like to share with you today are 9 principles or laws that we have found guide effective systems engineering. The first law says that we keep the systems perspective. This means that we have to keep the end in mind. We begin with the end in mind. That's where the systems perspective comes from. Our end is to serve the customer, to meet the needs of the customer. When President Kennedy first announced that we would land on the moon within the decade, that became the end for those who would become the National Aeronautics and Space Administration and who would literally launch the space program. We needed to serve the ends that had been announced. In the same way, we have to serve our customers. So the customer's need is the end that we keep in mind. We have to know where we're going. Yogi Berra pointed out, if you don't know where you're going, you'll wind up somewhere else. And that's very, very true. It becomes especially easy in complex projects to lose our way, to lose focus on the ultimate destination as we deal with the complex problems that face us during the process. But our process serves the goal of satisfying the customer's needs in the long run. The process is our map to that destination. And just as in real estate, the principle is location, location, location. The principle in this prospect calls for perspective, perspective, perspective. And that perspective is the systems perspective. Our second law points out that it isn't helpful to solve the wrong problem. What does that mean? Russell Ackoff, who was a business professor at the Wharton School and one of the seminal systems thinkers in our world, pointed out that we fail more often because we solve the wrong problem than because we get the wrong solution to the right problem. We get off track when we fail to understand the problem. We have to understand up front what problem it is that we're tackling. That's how we know where we're going. It's not helpful to do lots of work coming up with an elegant solution to the wrong problem. Very often in meeting the individual difficulties that arise along the way, we can become tangled up in the process and lose the perspective on the problem because we didn't in the very beginning and all along the way develop an adequate understanding. So like the welder working on the wrong link in the chain, we tend to lose focus because we don't understand the problem. Albert Einstein told us that it was a perfection of means and a confusion of aims that's really very often our problem. Our third law asks us to keep in mind that insight is our goal. In model-based systems engineering, we seek to gain the insight that'll help get us to the right destination. We need to understand what the problem is. We just talked about the importance of understanding what problem, what question we are answering, and what we are really dealing with. We also need to understand all of the different domains that bear on that problem. So we need to understand what's going on in the requirements domain. What are the requirements? How are those requirements to be satisfied? We need to understand the behavior domain, the integrated logic that will ultimately govern our solution. We need to understand the physical architecture domain. We need to be able to see the behavior, the integrated logic allocated into the physical architecture to come up with a solution. And all along the way, we need to understand the relationships between those domains. Requirements are satisfied by behaviors, and behaviors are allocated to the components of the physical architecture. We need to understand those relationships because that's the way that we verify and validate in the fourth domain the solution that we're positing for the question. In model-based systems engineering, the model is the key to that. The model provides us with a discipline to get that understanding. The model allows us to focus on that insight, to focus on the problem and the solution, and to avoid things like the cognitive biases that arise as we look at something and see what we expect to see. It's the model that calls us back to seeing what really is and isn't there. Marshall McLuhan pointed out that a point of view can be a dangerous luxury when it's substituted for insight and understanding. And nowhere is that more true than in the world of model-based systems engineering. For those reasons, the model is the main thing, as law number 4 tells us. The model is our focus in model-based systems engineering. It's what provides the key leverage and what sets model-based systems engineering apart from other possible approaches. The model describes the system. This is the way we know the solution and the problem and how they fit together. If we don't model the problem, if we don't have an adequate consideration of the externalities and the needs that drive the creation of the system, then we tend to lose sight of them or make assumptions about them. The model allows us to describe that in detail and to keep our focus there. As we develop the solution, the model describes the solution that we're developing. The model makes the system view the focus. Keep in mind that a model is a simplification of reality, and that's kind of tricky ground. A model simplifies reality, but how much should we simplify? We have to be careful because we can simplify so much that we break the connection with the reality. So the model that we construct has to be complex enough to describe all of the relevant aspects of the reality. I'm reminded of the story of the dairy farmer who was having problems with his cows not giving enough milk. And he had talked to the other dairy farmers living around him, and nobody seemed to be able to come up with any kind of a solution to his problem. So he decided, I'm going to go to the smartest guy in the whole area. And that happened to be a physics professor who lived on a small farm down the road. So one day he went down to the physics professor and said, look, I've got a problem. I wonder if you could help me. And he described the milk production problem to the physicist. And the physicist scratched his head and said, you know, cows don't come up often in my world, but I'd be happy to give this a try. If you'll give me some time, I'll get back to you. So the farmer thanked him and went home. A couple of weeks later, up the road comes the physicist. He greets the farmer and says, well, I think I've got something that'll work for you. The farmer said, great, what is it? And the physicist said, well, first you have to assume a perfectly spherical cow with milk homogeneously distributed throughout. And of course we know at that point that model is simplified to the point where it breaks with reality. Nothing that's going to be said by the physicist beyond that is going to be very useful because the model has broken. The documents that describe the model in model-based systems engineering flow from the model. We don't use documents as the basis of the model. And as we'll talk about a little further along, it really doesn't make sense to say that even a robust set of documents become the model. Rather, the documents flow from the model, and we'll talk more about that when we talk about views of the model. Law number 5 tells us that in order to catch a system, you have to think like one. That is, in order to design a system, we have to think in terms of a system. Here, we are the victims to some extent of the Enlightenment. The Enlightenment sponsored the notion that we could solve problems through analytic thinking. And analytic thinking means taking a problem, taking a situation, taking a posited solution, and taking it apart, breaking it down, and trying to understand the system by understanding the parts. Analytic thinking is very valuable, and it's the basis of the scientific method that developed out of the Enlightenment kinds of thinking. It's been taken to all kinds of extremes, but it involves breaking the problem down. The most enthusiastic child of the Enlightenment that I know anything about is my youngest brother. When we were growing up, if he got a present, a toy, a bicycle, he didn't do what my other brother and I did, which would be take it outside and play with it. He would immediately begin to take it apart, see if there was a better way that it could be put back together, to study it, if you will. We quickly learned as we got to be elementary school age that you needed to hustle home from school, or you would find all three of our bicycles disassembled in preparation for them being reassembled, usually in a way that introduced a capability for his bicycle that wasn't there before. But he tore everything apart into its component pieces and developed a good deal of understanding in that way. But analytic thinking alone, taking the system apart and looking at the pieces, won't get you completely there. Russell Ackoff says if you want a demonstration of it, think about trying to answer the question, why do automobiles drive on the right side of the road? Can you answer that question by taking an automobile apart? No, you can't. You have to engage in thinking that talks about the interaction of the automobiles and their environments. So analytic thinking alone doesn't get us there. What gets us there is when we hook analytic thinking to synthetic thinking, when we develop the ability to think about a system. Look at the definitions, in particular the Nkosi definition of a system. And the thread that runs through the different definitions in common is that the system is always capable of more than the capability of the components all added up together. In other words, the system synthesizes. There is a synergy with the system. The ability to see that synergy and to look at that system in that way is called synthetic thinking. If you can't engage in synthetic thinking, then you're susceptible to unintended consequences. Thinking about the components of a system and the way that they answer different questions in the problem without thinking about how they might interact together is the kind of thinking that brought us ladybugs to eat aphids on plants without thinking about the fact that rabbits can't hold a candle to ladybugs when it comes to reproduction, and that soon we would have swarms and swarms of ladybugs who can become a much bigger problem than aphids ever thought about being. That kind of unintended system interaction, system consequence, was the result of engaging in analytic rather than synthetic thinking. The sixth law tells us that it's all about relationships. Relationships describe how the system works. Relationships between the components, between the entities in a system, between the requirements and the behaviors, between the behaviors and the components. The relationships throughout the system are the essence of the system itself. System design depends on a meta model or a schema, which tells us what the possible entities and relationships are. When you add to that the attributes of the relationships and the attributes of the entities, then you can begin to make a living representation or model of the system. It's the relationships that provide the framework of that system. The entities, the functions, and the components and the requirements sit in isolation until they're webbed together with the relationships. They also provide the pathways for traceability. As we begin to look at what is related to what, the relationships provide pathways through the system that's being designed. The way to discover if all the requirements are fulfilled is to track them back through from the components through the behavior into the requirements. Components that are developed without a requirement as a justification behind the behavior that they perform represent resources wasted. Requirements that don't trace through a behavior to an ultimate part of the physical architecture are unfulfilled requirements and represent a measure of how the system falls short in that particular case. Law number 7 is a particularly important concept, and it's important because a lot of mistakes are made here. There's a lot of misunderstanding around this particular principle. Law number 7 says even a set of views is not a model. And I would amend that to say even a robust set of views is not a model. Why would we say that? Well, it has to do with the nature of the views themselves. We need to understand that a view of a model, a representation of a model, really is a specialized response to a database query. What's presented in any given view of a model, whether that view is the classic kind of activity diagram or a functional flow block diagram, it contains a subset of the information that's contained in the model, presented in a structured way. The same is true of documentation. A requirements document can be structured to meet standards for the document themselves, to be presented in an orthodox way, but they contain a subset of the information in the model. So they are responses to database queries, and they contain the subset, the information that's asked for in the query. The views flow from the model. There is a model behind the views in model-based systems engineering. They help us to understand the model. They present information, but they are not the model itself. If you don't believe that, print out a number of views and then try to simulate them. Try to get the views to simulate. They don't simulate because they're not connected. They're not webbed together. It's the underlying model which is webbed together, not the set of views. So if you have developed a robust set of views, you do not yet have a model, not in an executable sense. So we could put together all the documents, all the drawings, all of the particular views of a model. We could glom them together, and they do not become the model itself. The model is always the underlying entities, relationships, and attributes, and not the representation of that information in a particular view or set of views. The 8th law encourages us to choose the representation that best suits the audience. Here, the overriding consideration is, what's the purpose of making the representation? Whether that's to print out a diagram or to come up with a document, any way that we call up information out of the model, the first thing that we need to do is to align that representation so it'll meet its purposes. The purposes that any kind of a representation needs to meet are threefold. The first is, who is the audience and what will speak to them? If you take a group of acquisitions people whose concern is, what will this system do? You know, once this system is developed, what exactly is it that it'll do? And whose orientation comes from a world of flow charts and organizational diagrams. If you take that group and say, okay, I'll tell you what I'll do. I'll show them some IDIF 0 and N squared diagrams. They're going to become very, very confused. They won't resonate with the form of the views, and the information in the views therefore likely won't be conveyed. So the first consideration in selecting a particular view for presentation is, who are the audience and what kind of views will speak to them? The second consideration is, what do they need or want to know? The audience almost always comes to the point of looking at a view of a system, a view of the model, from a particular perspective. That needs to be considered. Why? Because until you jump that hurdle, until you've told them what it is that they want to know, they're not really ready to pay any attention to what it is that you want them to know, which is the third consideration. So you need to answer their questions, recognize, meet those up front, and answer the questions. And then you need to think about what it is that you're trying to convey. What is the reason for generating a representation or a view? So if we consider who the audience is and what will speak to them, what they want to know, what they want to get out of the presentation, and what do we want them to know, then we have a presentation that answers the mail. The ninth and final reminder comes in the form of the ninth law that says that systems come in threes. They always come together. If we're going to design or improve a particular system, we're really dealing with three different systems. The first system that we deal with is pretty obvious, and it's almost always gets a lot of consideration. Sometimes it's the only system that gets consideration. Be considered, and that is the system that's being designed. So in this case, we're looking at a subway system. If you were designing a train for a subway system, we'll almost never overlook the design of the train. The second system we might overlook, or we might not adequately look at, and that's the context in which our design is going to live. So we're going to design a subway train to run in a particular subway system. We need to understand that context. We need to look at that second system and not forget that as a part of our modeling process. And then the third system is the one that most often gets overlooked, and that's the process that we use to come up with the design. It's not overlooked in that everybody has a process for design, but it may not be well formed, and it may not be an intentional process. It may be one that simply has grown up ad hoc from the underlying context. We need to look at the design process, because that's where we get the discipline that keeps us away from unintended consequences, that allows us to live by the first 8 laws. They're embedded in this design process. There are other ways to parse this. Dr. James Martin has written an excellent article and recently gave a very good presentation on something that he refers to as the 7 samurai. And he sees 7 different systems that need to be considered, where I have 3 here for you today. If you look at it, you discover that his 7 systems, result from breaking out these 3 basic underlying systems. I commend that article to you. You can find it on the internet. It's a good article, but the thought process of thinking about these 3 systems, the design, the context, and the design process, help to keep us on target and actually help us to use the first 8 laws. So where have we been? We have begun with the end in mind in law number 1. We have experienced that it doesn't help to solve the wrong problem. The most elegant solution to the wrong problem is not going to be helpful. Law number 3 told us that insight is the goal, that we seek understanding through insight into the problem and insight into the solution. We learned that that came because the model is the main thing. The model is what helps us to gain the discipline to get the insight that we need. Law number 5 told us that to catch a system, you have to think like one. We have to think in terms of systems. We need to focus and keep the system view. Law number 6 tells us it's all about relationships. That's what makes the model, and it makes the model more real because it's the relationships and the interaction of the entities in the model and the interaction of the components and actors in the real system that make the system work. Law number 7 tells us that even a set of views, even a robust set of views, is not a model. Law number 8 tells us that we need to choose the representation that best suits the audience so that we can convey the answers to their questions and the information that we need to convey to them for our purposes. And finally, we're reminded by law number 9 that systems come in 3s, and that we need to think about not only the design that we're working on, but the context in which that design will live and the system by which we come up with the design. Here at Vitek, we are all about the system view and maintaining the discipline and rigor of true model-based systems engineering. We've provided this support through our software and our services and training, and through our research and development in a variety of arenas, and we stand ready to talk to you at any time in any way that we can help you. Here are some sites for more information to pursue this topic further or to talk with us about anything that you would like to talk about in the arena of model-based systems engineering. I invite you to avail yourself of any of these resources. And again, I thank you for your time and attention. I hope this has been helpful. So with that, Laura, I'll turn it back over to you.
Thank you, Zane. Now we'd like to move to your questions for our presenter. We've already received some great questions. Thank you for submitting those. I encourage you to join the discussion and submit your questions at any time via the Q&A function in the GoToWebinar window. Let's get started. Zane, we have a question from Mark. He asks, in Law 8, you were talking about our audience. What do we need to know from them?
Mark, I think there are several things that we need to know from the audience. The first thing is, who are they? That gives us an idea of what their perspective is. And it gives us an idea of what their usual context for communication is. So if you have a group of business process folks, their context, vocabulary, and conversation will be a lot different than if you have a room full of electrical engineers. So you first learn who they are in the sense of what their perspective is. Then you need to think about a related topic, which is what is their role? Why are they here? Why are they interested in this particular system or this particular design? That tells you the kinds of questions that they may have. The more accurately you can predict what kinds of questions they already have, then the more targeted you can be about your presentation. But it's basically about finding out what their perspective is and what their role is so that you know how to scratch the itch that they actually have.
Thank you, Zane. Next, I have a question from Sam. He asks, why isn't a complete set of views enough to make up a model?
Well, the trick here is that even if you have a complete set of views, if you will, you still don't have the webbing of the relationships between the views. So you don't really have the integrated logic. You have portions of the system depicted, but not to the point where you have a logic that hangs together and becomes executable. So you can get a good picture of what the underlying data is, but that's not a substitute for the underlying data, the model, the relationships, entities, and attributes themselves.
Thank you, Zane. I have one more question here from Ken. He asks, how could a model be too simplified to be useful?
Well, the way that a model gets too simplified to be useful is that it becomes so simplified that it disconnects itself from reality. You wind up with a model that simply assumes or generalizes in ways that mean that it doesn't really represent the underlying reality. If we're trying, for example, to develop a model of a piece of equipment that's going to move 8 tons of coal along an underground pathway where the ceiling height is going to be no more than 36 inches, we care about lots of things. We don't particularly care that the piece of equipment is painted yellow. So we can have a model that's simplified to ignore color, etc. But we can't have a model that's so simplified that it doesn't consider the ceiling height, for instance. So it has to be, how simple does it have to be? I had somebody ask me this recently in a presentation. So how simple should it be? Well, as simple as it can be, but no more. And you have to think about that a little bit. I got that from Pogo, by the way, but that's really the answer, and that is that it's simplified, but not in ways that make it irrelevant to the reality that's being represented.
Thank you, Zane. That wraps up the Q&A for today. If we weren't able to answer your questions during the Q&A portion of the presentation, we will contact you directly after the webinar to ensure that your question is answered. If you have other questions or comments that you didn't send in today, we invite you to post those on the forum of our community site. You'll find that at community.vitekcorp.com. A recording of today's webinar will be posted to our website, vitekcorp.com, by the close of business tomorrow. We would also like to personally invite you all to join us on Tuesday, June 19th at 3 p.m. Eastern for a special presentation titled 5 Steps for Improving Your Systems Engineering Practice by Zane Scott. In closing, I would like to thank our presenter today. I'd especially like to thank all of you for your questions today. As we bring this webinar to a close, a survey will open on your screen, either in a new browser tab or in a new window. Please take a moment to provide us with feedback on today's presentation and what topics you'd like to see covered in future webinars. Thank you all for joining us, and have a great day.